We live in the golden age of prediction. Today, artificial intelligence models can look at millions of data points and tell us what is likely to happen next with staggering accuracy. They can predict the next token or word in a complex sentence, forecast the trajectory of a stock price, or easily determine whether a pixel matrix belongs to an object. But there is a fundamental wall that pure statistical data prediction hits. A structural wall that separates mere superficial pattern recognition from genuine understanding. That wall is causality. Causal inference is the foundational science of understanding why things happen. It is the mathematical and logical framework that shifts us from observing two events happening together to proving that one actually created the other. Think about how humans naturally reason. A toddler does not need millions of experimental trials or big data tables of a hot stove to predict it will burn them. They touch it once, infer the invariant causal link, heat causes pain, and instantly update their world model. If we want artificial intelligence to reason robustly, act safely in unfamiliar territories, and step beyond narrow correlations, it must learn to climb this exact same ladder of cause and effect. You have probably heard the golden rule of statistics 1,000 times. Correlation is not causation. But despite hearing this warning, our human brains and our machine learning models continually fall into the trap of confusing the two. To understand why, let's examine a dataset showing two completely separate real-world events over time. Look at this chart. As ice cream sales skyrocket up and down, another completely independent metric follows it in beautiful, symmetric synchronization. Shark attacks shoot up in perfect harmony. The mathematical correlation coefficient between these two variables is nearly a perfect 1.0. If a standard, non-causal machine learning model looks at this data, it detects an undeniable pattern and optimizes for a flawed policy conclusion. Ban ice cream sales to prevent shark attacks. But you know that's absurd. Banning gelato on the boardwalk will do absolutely nothing to stop sharks in the ocean. There is a hidden, unobserved third variable driving both data pipelines simultaneously. Summer temperature. When temperatures rise, more people buy ice cream. Concurrently, more people choose to swim in the deep ocean, making them natural targets for marine predators. This shared systemic driver creates what we call a backdoor path. It generates a statistical illusion, a powerful correlation, where zero physical causation exists. If an algorithm relies blindly on these raw associative correlations without correcting for it, to navigate the world of cause and effect without falling into statistical traps. Pioneer Judea Pearl introduced a foundational paradigm, the ladder of causation. This conceptual ladder consists of three distinct mathematical and cognitive rungs. Crucially, almost all current machine learning algorithms are completely marooned on the very first step. Rung 1 is association. It is entirely about passive observation, seeing patterns in data. Mathematically, it operates via conditional probabilities, asking, given that we observe an event X, what is the likelihood of observing event Y? This level answers diagnostic questions like, what can a medical symptom tell us about a hidden disease? It requires zero comprehension of underlying biological mechanisms, relying purely on static correlation. It is the natural home of deep learning networks. To step higher, we must reach rung 2, intervention. This is the domain of active execution, doing rather than simply seeing. Here, standard statistics breaks down and we introduce Pearl's decalculus. The formula shifts to the probability of Y. given that we forcefully intervene and command X to occur. Intervention asks questions like, what will happen to a patient's blood pressure if we actively administer a new clinical drug? This cannot be inferred by merely looking at past passive logs, because taking action deliberately alters the environment and shatters existing observational correlations. Finally, at the pinnacle sits rung 3, counterfactuals. This is the rarefied cognitive realm of retrospective imagination. The mathematical notation becomes deeply complex, computing the probability that an alternative outcome Y would have occurred under alternative condition x. Given that we actually observed completely different historic facts, x' and y'. Counterfactuals force us to ask the ultimate question. What if? For instance, what if I had not taken that aspirin block? Would my painful headache still be gone right now? Answering a counterfactual requires a robust structural model of reality because we are comparing the actual physical history with a parallel, hypothetical timeline that never materialized. As we ascend from association, through intervention, up to counterfactuals, we move away from shallow data curve fitting and build systems capable of genuine scientific reasoning.
Let's see how this theoretical ladder applies to a highly practical domain: natural language processing and modern large language models. Imagine we feed an AI chatbot a standard customer product review containing conflicting sentiments. On rung 1, association, the language model operates purely by pattern matching data tokens it observed during its massive pre-training phase. It maps specific lexical tokens like died to a high probability of negative emotion and great to a high probability of positive emotion. It calculates a static conditional distribution, outputting a prediction without understanding why the user is upset. To step onto rung 2, intervention, we actively inject an instruction into the system prompt, disrupting the model's natural auto-regressive generation pipeline. We force a brand new condition. Rewrite this review to make it sound entirely optimistic. The model alters its state vector based on our direct intervention, generating an edited alternative. But does the system actually comprehend the physics of smartphone hardware components? To achieve true rung 3 counterfactual reasoning, the model cannot rely on existing text databases. It must actively construct two parallel world models simultaneously. It must contrast the historic reality where the user left screen brightness at maximum with a hypothetical parallel history where brightness was low, evaluating whether that singular action was the true structural cause of the technical failure. If an NLP agent can successfully process what did not happen, map the underlying mechanics, and accurately answer these what-if queries, it evolves from a shallow pattern matching engine into a genuine, robust digital thinker.